Welcome to another BIMSA member seminar. It's a pleasure to have Hao Wu, Professor Hao Wu from Tsinghua and BIMSA, who is going to talk about BPZ equations, multiple SLEs, and connection probabilities.
Okay, very nice to see people here. So this is my first time to give a member talk here. So I already sent this slides to Yuval, and Yuval complained that it contains too technical formulas. So I removed many formulas, but Yuval still complaining that they're too technical. So we will see whether it is too technical or not. Okay. So my talk will basically have two parts. So if we don't have more time, we'll just stop with the first part. The first part is we focus on this loop ON model. So the model, we put everything to be the simplest case. We just consider the model on the hexagonal lattice. And then for this model, this is a configuration of edges on this lattice. And for each configuration, the probability measure is given in this way. So first, we count how many edges are open in this configuration. And the second, we count how many loops are there in this configuration. And then this probability measure is pretty simple. So it is p to the power of number of open edges and n to the power of number of the loops. So in this model, there are two parameters. P, we call edge weight, and n, we call the loop weight. So the measure is very simple. And then the question is, can we see some critical phase in this model? So of course, how it looks at a large scale will depend on the parameter n and parameter p. And for this model, the conjecture is that this model will have two critical phases. So for each n, between 0 and 2, there exists a critical parameter PC, so that if P is smaller than PC, this is the subcritical phase. So it means that if you calculate point-to-point correlation function, or you count 2 points connected to each other, this probability will decay exponentially fast. And then there are two other interesting phases. One interesting phase is that when P equals exactly PC, this is a critical phase. So it is conjectured to be conformally invariant in the scaling limits. And when P bigger than PC, so usually we say this is a supercritical phase, but in this model, it is not. It is still critical. So the conjecture is that when P bigger than PC, this model is still critical, and the scaling limits of the system will become conformally invariant in the end. And if you know the language about SLE kappa, so there is a kappa corresponding to these two phases of the P. So one kappa is in the interval between A6 and 4. Another kappa is what we call kappa hat. It is between 4 and 8. It corresponds to the two roots of this n equals -2 cosine 4 over kappa. So one root between A6 and 4, and another root between 4 and 8. So this is a basic conjecture for the loop ON model. Yeah.
Questions?
So maybe it is better to see on the picture. Yeah. So for instance, this is a subset of the honeycomb lattice, and now our configuration is just a collection of the edges. Now we put a boundary condition on this polygon. So we are thinking about this model on this polygon with 6 boundary marked points. And our boundary condition is that this is alternating. So it means that from the edges from 1 to 2, there are all the edges inside the configuration. And the edges from 3 to 4, these red edges are also have to be inside the configuration. And the edges from 5 to 6 are also required to be in the configuration. And then for the number of the edges, we just sample according to the probability measure. So it means that in each picture here, we first count how many open edges are there. So how many red edges are there. Second, we count how many loops are there. And then this probability measure is that P to the power of number of the open edges and times n to the number of the open loops, here. So this is the model. Yeah, so it's better with a picture. So it's in the bounded domain, it's easier to define it in the bounded domain. Yeah. Okay, so this is one example of such model. And then maybe we can go back to the first page. And so now it's clear, the model is clear. So now fix n parameter between 0 and 2, and there exists a PC, a critical value PC, so that it will give you 3 different phases. If P is less than PC, this is the subcritical phase. And the P equals PC, this is critical. And the P beyond the PC, this is also critical. So this is not the usual thing we see in other models. Okay, so now, so this is a general conjecture about the loop ON model. Now let us explain what kind of conclusion is already proved. Okay, so this. Yeah, in the polynomial, yes, exactly. So for the subcritical phase, the correlation decay exponentially fast. But for the both of the critical phase, all the correlations decay polynomially. Yeah. And then now we can also draw this phase diagram of this model. So the horizontal line is the n parameter. So n is from 0 to 2 here, and the vertical line is this PC. Here, this is the this blue curve is this function. So 1 over square root 2 plus 1 over square root 2 minus n. So this is the blue curve. And according to this conjecture, we know that below this blue curve, it is a subcritical. And on this blue curve, it is critical. And in particular, we see that here is the famous Ising model. So it corresponds to n equals 1, and the p equals 1 over square root of 3. So Ising model is here. And according to the conjecture, we know that above this blue line, it is also critical. And here there are several famous models. Here, n equals 0, p equals 1 is the uniform spanning tree model. Here, this n equals 1, p equals 1 is the percolation model. And here, n equals the square root of 2, p equals 1 is the FK Ising model. So this model is a dual model to the Ising model. And here, there's another special dot. So these 4 models are the 4 models that we can already prove that they are indeed conformally invariant. So 1 on the critical line, and the 3 are above the critical line. And there's one more dot here. This is n equals 0, and the p equals 1 over square root of 2 plus square root of 2. So this is the famous self-avoiding walk. So it is also in this phase diagram, but it is not proved to be conformally invariant yet. Yeah, on the hexagonal lattice. So on the hexagonal lattice, we know this number here. But if you change the lattice, then this number is even not known. Yeah. Okay, so this is the background about the loop ON model. So this is the general conjecture, and this is the 4 models that we already know that they are conformally invariant. Okay, so this is the picture we already see. So in my talk, I will focus on this loop ON model in a polygon. So to make everything simple, so my polygon just have 6 marked points on the boundary. So this is a polygon with 6 marked points. And my boundary condition is that this alternating boundary condition. So it means that the edges from 1 to 2 are required to be in the configuration. The edges between 3 to 4 are required to be in the configuration, and edges between 5 and 6 are required to be in the configuration. And for the rest of the edges, I just sample the model according to this ON loop model. So I count the number of the edges, I counted the number of the loops, and each configuration has the weight that p to the number of the edges times n to the number of the loops. And here we see that after we impose this alternating boundary condition, and then we sample the edges inside this polygon, so we see that this 6 marked point will be connected by this loop configuration pairwise. So this 6 marked point will be connected by these loops pairwise in a non-crossing way. And for the 6 marked points, we know that if we connect them pairwise in a non-crossing way, there are a Catalan number of them. So the total number is 5. So as indicated in these 5 pictures. So if I impose this alternating boundary condition, I know that if I only check how these 6 points are connected to each other, there are total 5 possibilities. And now my question is, what is the probability for each of them to appear in my configuration? And here is the conjecture. So the conjecture is that for the loop ON model, if n is between 0 and 2, and the kappa is between 8 series and 8, so this is the critical phase in the first page, then we can predict the probability for each of them to appear in my probability measure. As the size of the lattice goes to 0, So this probability measure will be given by these three quantities. So here in this sub-index beta, so it means it encodes my boundary condition. Or you can see this one is just one particular boundary condition, but it can be more complicated. And for this alpha, so it means that my inside of the connectivity form the link pattern alpha, so the planar link pattern alpha. So for each given boundary data beta, and for each inside connectivity pattern alpha, as the size of the lattice goes to 0, this probability will converge to the right-hand side. So the right-hand side, in this right-hand side, there are three quantities. The first quantity is a constant depending on alpha and beta. So this is called the meander matrix. And the numerator here, so this is a function, in fact, depending on the location of the two unmarked point on the boundary. So this is a function in my polygon. And this is what we call the Coulomb gas integral. And this C alpha is also a function on the polygon. And this is called the pure partition function. And I will explain as a three
question. How can you squeeze the size of the lattice to 0? Then your boundary conditions would be violated. Because those edges will be outside of your consideration.
Yeah, so suppose I start with a fixed omega domain and I approximate this domain by my polygon with the 6 marked points. And then and the size of the lattice is delta, and then I let the delta goes to 0.
I see.
Yeah. Okay, so now I can predict this probability by these three quantities. So this is a very concrete formula. So, and I will show you what is the definition of these three quantities. Maybe this is where you complain that it's too technical. Okay, so first, this is the meander matrix. So the meander matrix, so it's a matrix, and the size of the matrix is a Catalan number by Catalan number. So there are two entries. So each of the two entries are encoded by this two planar link pattern. And at the entry alpha and the beta, the number is just n to the number of the loops in the meander of the alpha beta. So here we can already see that this is related to the loop-Owen model because it is counting the number of the loops in the meander. Okay, so this is a very big matrix. The size of the matrix is Catalan number times Catalan number. So if my marked point is a lot, then this matrix is very large. And then the question we are interested in this matrix is that whether this matrix is invertible or not. And this is completely solved. So the conclusion is that this matrix is invertible if and only if kappa has to be inside 0 and 8, but remove this rational numbers. So 4p over p prime. Yeah, so later I will show whether I'm interested whether it is invertible or not. Yeah, so I'm interested whether it is invertible, and this is completely known, and known very long time ago. Okay, second.
So
yeah.
Yes. Can I want to understand.
Yeah.
Can you explain again why I have 5 of these?
5, because for the 6 marked points, they are connected pairwise inside of the polygon by these loops. Right. So the 6 points, they've connected pairwise by this non-crossing curves. Right. So the total number is a Catalan number.
Okay, got it.
Yeah. The meander. Okay, so the meander is that. So I first draw my alpha in the upper half plane, connecting pairwise of the two endpoints, and then I also draw my beta in the same way, and then I take the horizontal reflection of beta and put it on the bottom of alpha. This is called the meander of between alpha and the beta, and here I count how many loops are there in this meander. So in this example, there's only one loop.
What should this matrix tell you?
What?
So why is it of this form, n times to the number of loops?
This is the definition of the matrix, and we will see later that it will give us the coefficient between two systems, the solution to the BPZ equation. Yeah.
She just finds a way of keeping track of loops in the model. And this matrix tells you that, obviously.
Yeah. Okay, so this is the meander matrix. Second is the Coulomb gas integral. So by the name, we see that it is a big integral. So this integral is defined in this way. So first, we fix the two endpoints in the increasing order on the upper half plane. So they are just marked points. And then my integral function, so it is an n-fold integration from u1 to un. And the integrand is pretty simple. It's just a polynomial. So it's of this form. So us minus ur times ur minus xi. So the integrand function is pretty simple. And the integration surface is that for u1, I integrate from xa1 to xb1. And for un, I integrate from xan to xbn. So this a and the b's, they are the pairs in this boundary data beta. Okay, so this is the integration surface. So it is a very explicit integral. Okay, and now we see that this integrand function, in fact, it is complex valued. So in order to specify what we are integrating, so we have to specify which branch we are using for this multi-valued function. And the branch we are choosing is that it is chosen to be as positive as possible. So we want it to be positive. And in the end, we also desire this integral is eventually positive, but it is not clear at this step. Yeah, so the boundary condition is also a planar link pattern beta. So it's a pairwise relation between the two endpoints. They are paired, yeah. Hmm? Yes. XA1 is a point on the plan. XA1, A1 and A. Yeah, so they are just from 1 to 2.
A1, B1, it means XA1, XB1 are connected by an edge.
Yes. Yeah.
Okay.
Yeah.
It's the red edges, basically. Am I right?
Yes.
Okay. Mm-hmm.
Yeah.
Red parts.
Yeah.
Paths.
Yeah.
Paths.
And the number of integrals has to be always n.
Yes. Yeah. Okay, so this is the definition of the Coulomb gas integral. So where does it come from? So I didn't invent them myself. So they come from a representation theory of Vehusar algebra. So physicists, they are very smart. So they check this BPZ equation, and they guess that this solution to this BPZ equation should have this form. So, or they say that if you take this form, you can check that they are the solution to this BPZ equations. So basically, in fact, it is not so hard to check that they are indeed a solution to the BPZ equation. Basically, just switch the order of the differential operator and the integration surface. And then you can check that they are indeed the solution to the BPZ equation. But of course, they are not guessed by me. So they already exist a long time ago. So they are predicted by the physicists that they are the solution to the BPZ equation. And then the question we are interested in those equations are, so first, whether they are always positive. Because in the end, we want to show that this function will give us a probability. So before it is a probability, it has to be positive at the first place. And then we investigate whether they are positive or not. So they are well defined for kappa between 0 and 8. And however, they are only positive when kappa between 8 and 8. And when kappa equals 8 and equals 8, in fact, they vanish. And we even know how fast they go to 0 as kappa approaching these two endpoints. And when kappa is less than 8, in fact, we know that they can switch sign on the definition of the domain. So in fact, this is out of the framework of the loop-Owen model. And this also explains that this loop-Owen model only works from kappa between 8 and 8. Yeah. Okay, so this is the Coulomb gas integral. And the last quantity we call pure partition function. So this is also a collection of the solution to the BPZ equations, but this collection of the solution is characterized by their boundary data. So in the previous Coulomb gas definition, they are just explicit integral formulas, and then we can check that they are solution to the BPZ equation. And for this pure partition function, they are not defined explicitly, so they define in the way that they are solution to the BPZ equations, and they satisfy certain prescribed given boundary condition. Yes, using exactly the same kappa. Yeah, so there's already this cosine relation at that time. Yeah.
Why do you, in the original formula for energy, why do you have 1 over? Why is it in the denominator? Ui minus uj.
You mean this denominator?
Yeah.
You mean this boundary data, this
Yeah, the
equation?
previous slide,
The previous.
when you're integrating,
Uh-huh.
why are these terms, you say that one? Yeah, kappa is positive, right?
Yeah, kappa is
Okay.
between 0 and 8.
Okay, so there you go. That's why is it that, why do you have things in the denominator? Why do you have meromorphic functions?
Why? So if you really want to check that this is a solution to this BPZ equation, you just switch the order of the integrated surface and the differential operator. Yeah.
Philosophical.
Why the first terms come with the positive power when they use interaction themselves and when they use the negative interaction with the negative power?
Exactly. That's the question. That's the question. Like, where
Okay.
is this coming from?
I don't know. Yeah.
Oh.
But if you want to invent more solution to the BPZ equation, basically you can change those parameters. Yeah, so, but these ones are the well-chosen one that we find that they fit in this loop-on model conjecture. So basically those numbers can be, you can vary them if you want to.
As that charge, they have different charges and the others have the same charge. Yeah. This is a right. I mean, this comes from the vertex operators.
Okay. All right. Okay. Okay.
Yes.
I'll ask him
Yes.
or you.
Say it again. Okay. Yes, I should put the full name. So there are the three names. The first initial of the three names, and they are very long. Yeah, I can't write them on the blackboard because they are very long. Polyakov. Yeah. Yeah, sorry, I should have put the full name there. Yeah. Yes, so this is the Coulomb gas integral. So it's just defined in a very explicit way as an integral. And for the third quantity, we call pure partition function. So they are also solution to the BPZ equation, but they are characterized by a particular chosen boundary data. And this boundary data, in fact, in the probability meaning, so it is clear that, so remember that we want to calculate the probability for several curves connecting among each other. So for instance, we want to calculate this picture. And if these 2 points, they are very close to each other, what do we expect? Of course, we expect that when they are very close to each other, the probability of the 3 curves will converge to the probability of the 2 curves. So this is from the motivation of calculating this kind of probability. So this system of probability should have certain compatibility. Like when you shrink 2 points, then the probability for n curve should converge to the probability for n-1 curve. And this boundary data is chosen exactly in the way that we want to match this compatibility. Okay, so of course this is the motivation. Yeah. Yeah, the PDE corresponds to the BPZ equation, and the COV is the conformal covariance. So we require them to be conformally invariant. They're conformally covariant. Yeah. So it is. Yeah, this ASY is the asymptotic property here. Yeah. Yeah, so this is the idea why we choose this particular boundary data, because we want to match this compatibility. But then it is not clear that after impose this boundary condition, there still exists a solution with your prescribed boundary data. And now the conclusion is that when kappa between 0 and 8, in fact, there exists a unique collection of pure partition function having the prescribed boundary data you want. And here I list the references for this existence and the uniqueness result. So there are a long list of the existence and the uniqueness. The first appeared is with the uniqueness. So it was in 2015. And then for the existence of such a solution, so there's a long history. So there are many literatures, and each one construct some of the solutions, but with different range of kappa. Yeah, but in the end, now the conclusion is that this collection of function, they exist and it is unique for all kappa between 0 and 8. Okay, so this is the pure partition function. And now it comes to our question. So this collection of pure partition function, so in fact, they form a linearly independent, and they form a basis for the solution to the BPZ equation. And they are always positive. So this is different from the Coulomb gas. So they are always positive. And then when kappa goes to 8, it will vanish. And then we know the rate that it goes to 0. So it's at the rate 8 minus kappa to the power of -1. And then when kappa goes to 0, in fact, it will decay exponentially fast. So this is not my work, but this is already known that if kappa goes to 0, in fact, it decays exponentially fast. When kappa goes to 8, it decays to 0 polynomially fast. Okay, so this is the pure partition function. And now, yeah. No, so usually they're not explicit. So in a very special value kappa, like kappa equals 2, 4, and 8, they're explicit. But beyond them, they are not explicit in general. Yeah. They can't be explicit. So it depends. So for instance, if there are only 4 points, basically you can solve them explicitly. And then in fact, they are the solution to the Euler's hypergeometric function. So if you think this is already not explicit, yeah. So now we see that this Coulomb gas integral, they are solution to the BPZ equation, and the pure partition function, they are also solution to the BPZ equation. And we know that pure partition functions, they form a basis of the solution space. So therefore, the Coulomb gas is a linear combination of the basis, right? And this linear coefficient is given exactly by this Meander matrix. And here we see that why we're interested in is whether this matrix is invertible or not, because we know that pure partition functions, they are linearly independent and they are basis. And now maybe you want to ask whether the Coulomb gas is also a basis. And then whether it is a basis or not, it is encoded completely by this matrix. And of course, if this matrix is invertible, it is a basis. And if this matrix is not invertible, no, they are not, because they are linearly dependent. So that's why we are interested in whether this matrix is invertible or not. Okay, so now we can go back to this conjecture. So now I have already introduced the 3 quantities. Now we go back to this conjecture. So it's that we consider this loop ON model in this polygon, and we want to calculate this probability. And the conjecture is as delta goes to 0, this probability was given by the product of the 3 terms in the right-hand side. So this is the general conjecture. And we know that for the loop ON model, there are 4 models we already know that they are conformally invariant. So they are Ising model, FK Ising, percolation, and the uniform spanning tree. So these are the 4 models we already know that they are conformally invariant. And then for this 4 model, you can ask whether this conjecture is true or not. And yes, the answer is yes. So for these 4 models, we already know that they are conformally invariant. We can also check this conjecture. So this formula is true. And in particular, they are very interesting phenomenon. So here, if you plug in kappa equals 6, and then you're going to find that this Coulomb gas integral is always 1, regardless of the boundary data. So it has nothing to do with boundary data beta. So this is, if you are familiar with this statistical physics model, so this is related to the fact that this percolation has nothing to do with the boundary data. So it is independent of the boundary data. So this partition function is always 1. And there's another interesting value is that if you plug in kappa equals 3 in this Coulomb gas integral, and it has an explicit formula. So it is a Pfaffin between xj minus xi, and it has nothing to do with boundary data either. So there's no beta in the right-hand side. So this is these 2 values, they are very special. So in fact, this is also related to another famous conjecture is that the high temperature Ising model is conjectured to be percolation in the scaling limit.
Cool. Another question. What is significance of kappa? What does it measure? Or I could have asked the same thing about n. Why is n chosen that way?
So n is a parameter between 0 and 2. So
Sure.
it is important to choose, and it is more important to choose p. So PC, so this is the critical line for PC. So this is a function in n.
Okay, but
Yeah.
I can choose n many different ways between 0
Yeah,
and
so for instance, so in fact, in the physics, in the full conjecture, n can be between -2 to 2.
But what is n measure? What is this parameter measuring about the physical system?
So it's the loop weight.
Loop weight.
Yes. And as a probabilist, I don't understand how to make sense with a negative n. So because then my probability measure is not positive. So I don't understand how to make sense of -n. But in fact, in the physics literature, the conjecture is about n between -2 to +2. And yeah, the important conjecture is that, so as we all know that for the critical Ising model, it is conjectured to be conformally invariant in the limits. So it means that you have to be on the critical temperature. But suppose you are above the critical temperature, it's a high temperature Ising model. And if you consider the high temperature Ising model on the hexagonal lattice, the conjecture is that it will also become conformally invariant in the end. And the limit is the same as the percolation. Yeah, so this is another conjecture about Ising and the percolation.
High temperature, but you're not fixing the temperature and scaling. So
yeah, so for any fixed temperature, but above Tc, then the conjecture is to be percolation. So suppose your temperature T is infinity, then this is exactly percolation model. And the conjecture is that as long as the T is bigger than Pc, then it is always the same as the percolation in the limit. Yeah, this is this is a famous conjecture between this point and this point. Yeah. Okay, so this is the first part. So do I still have time? Okay. Yeah, so I don't know how long it will take. So I also prepared the second half. So if there's more time, I can continue with the second half. Yeah, so the second half is that there's 4 models that we can prove this conjecture. So there is one point here. This point is very special. So it is special in many sense. So the first thing that it is special is that when we look at this Coulomb gas integral here, so we know that they are positive for kappa between acers and 8. And there's something special at acers and at 8. So in fact, in the physics literature, it is conjectured that for these two values here, so the two acers and 8. So its conjecture is that so these two values they are very important. They are special in the sense that the conformal field behind the model is become logarithmic conformal field. So this is very different from the Ising model. So there's a conjecture from the physics literature. And my second part is to make sense what is the meaning for the logarithmic conformal field behind the kappa equals 8 model. So this is the focus on the second part. So now I can move to the second part. So there's something special at 8 and acers. But for the acers, because we don't know the conformal invariance of the uniform spanning tree, so we didn't investigate here. But for 8, we do know the conformal invariance of a uniform spanning tree. So we investigated more here. So uniform spanning tree. So in fact, the uniform spanning tree is a special case of the loop model, but of course, we can define this model directly. So this uniform spanning tree is So it's a model on a finite connected graph, and we sample the edges so that they form a spanning tree. So it means that this configuration of the edges is a tree, and it covers all the vertices in this graph. And then so the total number of such trees, they're finite, and then we define a uniform measure on this spanning tree model. So this is called the uniform spanning tree model. And now we look at the same question for this uniform spanning tree. So for a fixed graph, we consider this uniform spanning tree in a polygon. So there are 6 marked points on my polygon on the boundary. And with the alternating boundary condition, in the same sense that all the edges from 1 to 2 have to be contained in the configuration. And all the edges from 3 to 4 has to contain in the configuration. And all the edges from 5 to 6 have to be contained in the configuration. And then I sample my uniform spanning tree model. Okay, so for instance, this is one example of the boundary condition and the inside of the connectivity pattern. And if we go back to this general conjecture for this connection probability, so we can repeat it here again. So if the size of the lattice goes to 0, for each fixed boundary data beta and for each inside connectivity alpha, this probability will converge to a scaling limit. And this scaling limit has exactly the same 3 quantities as before, but each quantity has a hat. So the reason is that before we send kappa goes to 8, all of them are positive. But all of them will become 0 when we set kappa goes to 0. So in order to get something non-zero, so we need to normalize them properly. And because as we already know how to normalize them properly when kappa goes to 8, so then this hat version are the renormalized version so that they are positive. And then this formula still holds. Okay. So this is meander matrix. This is the renormalized meander matrix. And this matrix is always invertible. And this F hat is the renormalized Coulomb gas integral. And this Z hat is the renormalized pure partition functions. Okay, so this is the formula for the particular case of the uniform spanning tree. And this is the key steps in the proof, but I will show the more interesting page. So the more interesting page is how it is related to logarithmic conformal field theory. So now what we want to check is that we want to check what is the asymptotic of this Coulomb gas integral. So we already know what is the asymptotic of the pure partition function. Now we want to check what is the asymptotic of the Coulomb gas integral. And the conclusion is that before we send the kappa goes to 8, they are always expand. So the expansion is always like a polynomial expansion. But after we send the kappa equals 8, we take the same expansion. So suppose x1 and x2 are very close to each other. We want to check how it goes to 0 or how it is explode as the 2 points are shrinking together. And then this function will have a logarithmic correction in the leading order. So this is very different before we send kappa goes to 8. And when kappa equals 8, there is a logarithmic correction in this Frobenius series expansion. And we compare it with the physics literature that there's a very concrete physics literature calculated the operator product expansion of the anticipated field phi 1, 2 when the central charge C equals -2. And for this OPE expansion, so it has this form. And this exactly coincides with the logarithmic correction we find there. So this is how we find this connection to logarithmic conformal field theory. But of course, it's just the first indication that the model behind the uniform spanning tree should relate to logarithmic conformal field theory because there's some logarithmic correction. But still, we don't know the precise connection to the logarithmic conformal field theory yet. And also, we want to understand what is the allomorphic observable for the uniform spanning tree in terms of the CFT. But this is also not clear so far. Okay, so this is the end. Yeah. Yes, so if you focus on 4 points on the boundary, so this function are explicitly given by hypergeometric function, and there you can already see the logarithmic correction, and this is also true for when there are more points.
While for the other cases, they didn't have logarithms. those the hypergeometric solutions.
Yeah, yeah, yes, exactly, yeah.
So first, let's thank.
Questions?
Yes.
Wait. There's someone here. Give me a second.
Okay.
Thank you.
Yes.
So maybe I'm lost somewhere. Can you elaborate on how on why you choose to consider that boundary condition where you consider 6 vertices and you connect them by pair?
Yeah,
or it's
so
just
the-
an example.
Yeah, the reason is that, so when we try to calculate this probability, we want the probability will have certain compatibility in the sense that if the 2 points are shrinking together, the probability for n curve should be compatible to the probability of n-1 curve. And if you believe, so it's first you believe this formula, this conjecture is true, and then you know that the formula has to have certain compatibility. And this compatibility give us exactly the boundary data we choose for the pure partition function.
Okay, thank you.
Yeah.
Okay, you
So in which of these of your theorems do you use S.L.E. and stochastic integration techniques?
All of them have to use it. Yeah. So in fact, here there's a list of the key steps in the proof. So basically, in all these frameworks, we need 3 steps. The first step is that we need to identify the limit of a certain proper chosen holomorphic observable in the discrete. So in fact, usually the first step is pretty hard because you need to find a proper one. So you can find several of them, but you need to figure out which one is good for your question. And then after you figure out what is the limit of the holomorphic observable, and then you solve the law of the interface through the Loebner chain, and you will see the driving function, the Coulomb gas there. And for the third step, you can show that the ratio between these 2 solutions to the BPZ equation will give you a martingale. And then you need to refine the analysis on the martingale and then use optional stopping theorem to prove the probability.
So a martingale in what parameter?
In T. Yeah, the T is the parameter encoding the interface. Yeah.
Yes.
How much of your techniques are lattice dependent?
The first step.
So if it's
Yeah,
another
so-
lattice, it breaks immediately, or it's
Yes, it breaks immediately. So all the proof, so basically all the proof, so the most important step, the first step. So the first step is a generalization of the original proof that they prove the conformal invariance. And that's the part, in fact, it is in principle, we believe it is true for all lattice. But the existing proof is very delicate to the lattice you choose.
so
Yeah.
it all goes back to Smirnov's.
Yes, yes, yeah.
But for Ising, it's no limit that we have to perform that.
But it have to be isoradial, and then basically it's the same as Z2. Yeah, it is equivalent as Z2 then. Yeah, so now I think the most general setup is isoradial graph. And then because you are isoradial, you define the holomorphic observable in the same way as Z2. So basically it's the same as before, yeah.
It's more general than percolation, where it's still not.
Yes, yeah. It's more general than percolation, but it still have to be isoradial, yeah.
Sorry, I want to ask something about the BPZ equation.
Yes.
So according to probability measure, it looks like the minor matrix is the number of configuration of all non-intersecting loops. And the right-hand side is just like exactly the solution of the probability measure of each configuration. So why this goes to this BPZ equation? This equation looks like the first term is a heat kernel of random walk, and
Yeah, so in
the
fact
last,
it is, yeah.
the one with xj minus xi squared looks like you give it a potential which force the loops don't collapse. So what about in the middle?
Yeah, so if you look at this BPZ equation here, in fact, I'm missing one condition, one extra condition here to make the solution space to be as the number of the Catalan number. So in fact, it is highly non-trivial that why the solution space to this BPZ equation is exactly the Catalan number. So this is why there are many literatures there listed. So in fact, there is a huge analysis on this on the solution space of the BPZ equation. So in particularly in this first work about the uniqueness of the solution, so there's a detailed analysis of the BPZ equation and it's a dual space. So they construct the basis for the dual space and also the basis for the original space. So in fact, it is highly non-trivial why the solution space has a dimension exactly the same as the Catalan number. And now we are trying to generalize this BPZ equation to the radial setting. And now, in fact, we don't know what is the dimension of the solution space anymore.
Okay, thanks.
It's finite, but we don't know the exact number now.
More questions?
Let me ask you, coming back to lattices. So I understand that in hexagonal lattice, there are some miracle happening, which allow you to have exact holomorphic observables. But on other lattices, they hope to have something asymptotic, kind of almost holomorphic, which is not exactly, but almost. And then this control of how not holomorphic they are. Is it feasible? Or it is hopeless? Or what you would say about that?
Yeah, maybe you should ask Stas. So yeah, so I don't know what is the I don't know what is the current status on the generalization of the lattice. I think there is some progress, but I don't know the exact current status yet. Yeah.
Okay.
Yeah.
There is a universality in the sense that all the lines that go from the boundary to the bulk, they correspond to the operator phi12 independently on the lattice or
Yes.
of the lattice.
Yeah. Yes.
But that's a religious belief.
Yes. Yeah. Yeah.
Everything was believed long time before the theory.
Yeah, so I was also surprised when I checked the literature, like the invertibility of this matrix and the Coulomb gas, they already dates back to 1919. So even before the invention of the SLE. Yeah.
So there was very last formula with the three functions with heads.
Yes.
Right? And you also had the same formula for the three functions without heads.
Yes.
So the second without heads goes to the limit.
Yes.
Right?
Yes.
So you just want to know where the individual guys would
Yes.
go.
Yes.
That
Yes.
was the
Yes. Yes.
Okay.
Yeah.
More questions? So one confusion I have, shouldn't this conjecture on the curves, n curves going to n-1, be somewhat compatible with the conjecture about asymptotics of size of the lattice?
So in fact, all the formulas are already, well, first as the size of the lattice goes to 0. So this is all the conjectures are already in the continuum. So there's no lattice anymore there.
I see.
Yeah.
I see. Another question, why do you need these z's to be smooth functions? Are they even smooth?
So I don't need them to be smooth, but because they are solution to the BPZ equations, they are automatically smooth.
Okay, I
Yeah.
see. Got it.
Yeah.
More questions? Let's thank Hao. That's not a question. Let's thank her again.
Okay.